Today we will discuss another emerging non-volatile memory, which is a phase change memory, PCM. So this is outline. So first we talk about the overview and the principle, and then we talk about some device challenges, including the current scaling, multi-level, and the reliability issues with this technology. And we will end up with, again, the industry status in terms of the R&D of this technology, including the array-level integration and the chip-level demonstration. So first of all, the phase change material actually has a long history. Actually, you may have already used that in your daily life. Like for example, here, like even the CD, DVD, actually, on that disk is phase change material. So typically, the phase change material is made of this chalcogenide material. So chalcogen is, element in the group 6, except the oxygen. So the rest, this material is called the chalcogen. And then there like a compound is called chalcogenide. Okay. So then in the early 2000s, then this chalcogenide material was used for this phase change memory developments by the semiconductor industry. Okay. So the typical material is called the germanium antimony telluride, okay, GST material. And the typical ratio is 2:5 in terms of the compositional, ratio, right? 2:5. So this is the same class of material as I said earlier for the CD DVD. So the principle, okay, is that for the CD DVD kind of case, then the laser optically, is used to write or erase the data. So if you shine the laser to this material, then because of the high energy, right, then it will trigger the phase transition of this material from this so-called crystalline phase to the amorphous phase, okay? Crystalline to amorphous. So crystalline phase means, the atoms will have the long-range order. That means you have the crystal structure, okay? But then when you have the laser to get the high energy into the material, then it will heat up the material, then it will, be melt. And then after that, then the atoms will move around, and then it will have this disorder kind of, connection. So this is called amorphous state, amorphous, okay? So then you can also use low power laser to gradually, recrystallize the material. So the difference is that you need high energy to melt it, right, in a very short time. And then if you give no energy and a longer time, then you can recover from the amorphous to the crystalline phase. So here, then the DVD, you're going to, do this using the laser. And then also in the DVD case, the readout is also optical. So because the refractive index of this material will change depending on the phase, okay? So this refractive index, right? If you shine a light, then this reflection depends on the index of the material. So then if you can distinguish the reflection in terms of the angle and the intensity and so on, then that will be the mechanism to read out the data. So that's why in your DVD, right, the header, is rotating and to a certain location, and then if you want to read, you can shine a light and then detect the reflection. The reflection angle and the intensity will be different. That correspond to different data, right? So anyway, that is all optical, this DVD, CD stuff. But what we are interested in here will be the electrical programming and electrical readouts. Then that is the phase change memory, okay, for the semiconductor industry. Then we're interested in the electrical, okay, operation, okay. So electrically, this is similar. So as I said earlier, so no matter it's a CD or electrical, what you are going to do is locally heat up this material. You have two temperature, okay. One is called the melting temperature. One is called the crystallization temperature. So in the program, let's say from the program phase or write phase, you are going to apply, no matter which way, electrically or optically, you need to generate this temperature profile within this material to melt the material. Then you create this from the crystalline to the amorphous states. So you have to do this in a short period, because once you melt the material, the atoms will move around, and then you need to do this quench process. So here you need this quench, means you remove the heat source right away, very fast. Then the atoms will not have time to go to the ordered location. Then they will remain at this random location. So from the energy point of view, actually the system will have lower free energy when, let's say, the atoms are in the crystalline phase. That's a more stable phase, actually. When the atoms are, in this ordered phase, then the system energy is lower, okay? So, but then when you do this quench process, because the atoms do not have time to go back to this original state, they will remain at this random location. It's like they are trapped in this energy minima. But this energy minima is not the lowest global minima of this free energy of the system, okay? So then if you give this material a lower temperature profile like this one, then you can help the atoms to move around a little bit. Then that will help this to jump over this barrier and then go to the crystalline phase. That is this recrystallization process. Okay. So it's basically a thermal process in this material. So here, for example, this amorphous states, people usually call amorphous states. If you gradually ramp up the temperature, you see the resistance or resistivity of this material gradually go down to the crystalline phase. Okay, so always the amorphous state correspond to higher resistance, and then crystalline phase correspond to a lower resistance. So here, the crystallization temperature is like 200 C, something like that. Here, for example, this one, they say 200 C. And then this one will be like 400 or even 500 C, okay? So you have those two temperature. Okay, so here we're interested in this electrically programmed phase change memory. This is not the CD-DVD, okay? So we're going to apply large currents to trigger the high temperature due to the Joule heating. You are going to transition from the crystalline to the amorphous states with the quench process. And then with the medium current, you generate some lower temperature to help recover the crystalline phase or recrystallize. Okay. So then you are going to use a super low current or super low voltage to sense the resistance. So basically, this is like your reset process. This is your set process. Okay. And then this is a read process. All right. So any questions so far? Okay, so let's look at how the device is fabricated or integrated in the semiconductor process. So here, this is a typical phase change memory cell called mushroom cell. Mushroom. Because it's like a mushroom. So here, this is your GST material, okay? this layer, you deposit that, but you need a bottom electrode, and then here this is a plug or contact wire, like a plug or contact wire. And then you have a top electrode. It's a two-terminal device. So this plug basically is like a built-in resistor with some metal, you know. The goal of this one is to generate the heat because your current flows through here. You're going to generate the heat, okay? Pure heating, basically. This heat will melt this region, okay? This is active region of the device because the heat, you know, will dissipate, right? The temperature, I mean, you will have a gradient. So the high temperature to the low temperature will have, you know, a gradient. So then only the temperature higher enough, for example, higher than that 500 degrees C, will melt this region. So this region will change, right, from the crystalline to the amorphous state. And then if you apply a lower current, then you can recrystallize from low to high. Oh, sorry, high to low resistance states. So anyway, this is the device structure, okay? So let's rely on, again, the dual heating through this plug. So here, let's look at some animation. So as I said, so eventually you want to generate this kind of temperature profile, right? This is the melting temperature you are going to reach. So this reset process, let's say you apply large current through this crystalline. So here, this is a crystalline phase. And then you apply large current, then we generate high temperature, and then temperature will locally melt this part. This part will become amorphous state. So the device will go through here this temperature like a profile like this. So this part, you quickly remove the power supply or you remove your current. Then this is a quench process. You have to do this fast. Otherwise, the atoms will not remain in that random location because atoms tend to go back to the, you know, the ordered location. The only reason that they remain at this random location is because you remove the heat source right away. They don't have time to go back to the preferred, you know, ordered crystalline phase. So here then to set, let's say recrystallize, you have to apply low, you know, temperature profile, but give a longer time for the device, for the atoms to move back to the preferred location, which is this ordered crystalline phase. Okay. So here we have some animation. You can see that. So here is some simulation to show this temperature, let's say current pulse, and then the corresponding temperature in this structure. Okay, so here we have this plug. As I said, it's like a local heater. You pass current through, right? Current through here. And then you generate this temperature gradient. So here, for example, you apply 400 micron current through the device. Then you have to ramp up the current. You see, this current, this increase. And then you see the temperature become higher and higher, right? So as we ramp up the current to 600 micron, then you see this one, and 800 micron, right? So here we are at the peak, right? So you see the temperature profile. So here is this temperature maybe over like 500 degrees C locally. This is at another scale, okay? So then after that, you quickly remove your current supply, okay? Then the atoms will remain. So here is like this active region, or sometimes people call it like a dome, like a dome. So then this region will become amorphous, but other regions still remains a crystalline, okay? Because the temperature, you know, will decrease, right, as you move away from the heater. So then only the regions near the heater will will become amorphous. Okay. So then this is the transition from the crystalline to the amorphous state. And then the set, which is the other way around, we have to apply a low current profile like this. Okay. So then you see that there will be some conduction path through this amorphous states, and then there will be current flowing through, but this current amplitude is small, so you will locally heat up a little bit. That will help the atoms to move around and then go back to the original crystalline phase. But then you have some, percolation path, and then it will help, recover this region. So after that, then you will have at least partially, recovered the crystalline phase. Okay. So this is through some atomic simulation. Okay. So here the timing is important. So as I said, this quench process, you need to remove the current very fast. So typically less than 10 nanoseconds, you can do this reset from the crystalline to the amorphous state. And then the set, you need to give a longer time for this to recover. So this requires nucleation and recrystallization. So like 15 nanoseconds, typical timing. Okay. So this is the programming and this is a programming operation. So that's why I said here the thermal time constant is a few nanoseconds. So even you remove the power supply, then you need a few nanoseconds for the system, for that region to cool down, right? So a few nanoseconds, right? Thermal RC time constant. Okay, so here are some real data measured. So here, this is a so-called the typical programming curve for the phase change memory. So what you will have here, for example, for the reset curve, which means you start with no reason state, which is crystalline phase. Actually, people have done some nice metrology work. That means look at the atomic structures under the TEM, the transmission electron microscope. So here this is a plug, and then they look at this region, and then they do this electron diffraction. So it has this pattern, this ordered pattern. That is due to the electron, scatter with the atoms here. So if you have electron diffraction pattern with this dot dot dot, that means this is crystalline phase. The crystal structure is reflected by the electron diffraction. So then as you ramp up the current and then do the reset, let's say 40 nanosecond or so. So when the current is high enough, then the resistance will be, after that, the resistance will be high. So for example here, after this reset, when you see that this region actually will be a little bit different from the other region. So you see amorphous phase, which means a very random phase here. So this is known like a repeated pattern. So if you do the electron diffraction, you don't see this dot dot dot. It's like a in this case you don't see that repetitive pattern. So here this is really amorphous state. So actually depending on the current, you see that, for example, here you apply like 400 micron, you get some intermediate value. So that's because here this amorphous region is kind of small. But if you increase the current to 600 micron, then you see that this amorphous region is large. So here, this is the way how you get the multi-level states, right? So depending on the programming current, 400 versus 600 microamp, because here at 600 microamp, you are going to get higher current, higher temperature. So the temperature gradients, or let's say this temperature gradient will extend further away. So you create a larger dome here, right? So then you can get multi-level states in this case. And then you can do the set curve, which means you have to apply low programming current. Then you can gradually, if you start with this high resonance state, the amorphous state, then you gradually also can recover this part, okay? But until here, you have to limit the set current. If you go above this 400 microamp, again, it will reset right away, right? So you have to limit the current, right? For the set, for example, you have to limit the current below, let's say, 250 microamp. And for the reset, you want to make the current larger than 400 microamp. So the current amplitude will matter to determine the transition high to low or low to high. So that's why here, this is unipolar switching. It's not the positive current or negative current, positive voltage or negative voltage. This is by the amplitude. Because no matter current flow this way or the other way, I square R is about Joule heating. It's amplitude. It's not the direction of the current. This is a unipolar switch. Okay, this is different from R1 or M1 we're going to talk about, or even FE ferro. That really depends on the voltage direction or current direction. So here then, if you measure the IV characteristic in the quasi-static sweep, so typically, this is not the real way to operate the memory, but if you want to do it, you can still do it by the quasi-static IV sweep. So here in this case, I think this is a sweep the current instead of sweep the voltage, because you have this snapback. So you can only get the set process from this IV characteristic in the DC kind of sweep. If you start with high resonance state, the amorphous state, the current is low, and then until here the current high is high enough, then you trigger the set, and then you have the snapback because resistance changes from high to low, and then you continue this one. And then you can sweep back, the device will go to the low resonance state. Okay. But it's difficult to show the reset here. Actually, you won't see the reset in the DC sweep. Why is that? Any idea? In the DC sweep, you won't see the reset. Actually, you cannot reset the device in the DC sweep. Because we said earlier, the reset is a quench process. You have to remove the current very quickly. In the DC sweep, in the typical measurement system, take like each step like a millisecond, and then you sweep this voltage, take like a few seconds. This won't trigger any reset. Okay. So then let's move on. So as you can tell now, the key challenge for this technology is the current scaling, right? It's very power hungry because you rely on the Joule heating. Joule heating comes from that current flow. So you burn the power to trigger the switching. So the key challenge is how to scale the current, switching currents, right? So this is for the reset, because the reset, from the crystalline to the amorphous, right? You need the high temperature to melt. So how to reduce the reset currents? That is the bottleneck for the entire, power, right, of your memory array. So here, there are a few approaches. The first one is to reduce the contact area, so make the device smaller. So you don't need to melt a large area of the material, right? And then you can also engineer the device structure, right, to make the heat generation more efficient and also the heat dissipation is more localized. Okay. And then you engineer the thermal property, electrical property of the electrode and interface, and so on. And then, of course, I mean, the phase change material itself, if you can lower down the melting temperature, it's only 500 degrees C, you only need 300 degrees C to melt, then of course, then that will help. Okay. So here the simple scaling, right? If you stay with the GST 225 kind of material, then simply by scaling down the contact area, so this is like a nanometer square. For example, here, this 1000 actually means like 30 by 30 or 33 by 33, right? Nanometer square. You still need like here you say like 300 micron, or this is million. So here is probably like 400 micron, right? So even for 30 nanometer by 30 nanometer, it's kind of small, right? So because today, you know, as SRAM, you at 3 nanometer node. If you recall the number 0.02 micrometer square, that will translate to 100 nanometer by 200 nanometer to have that 6 transistor there. So here, if you do 30 by 30, then the current is pretty large, like a few hundred micron. You know, each transistor, if you have 1T1R, the access transistor, each transistor with a minimal W over L can only provide you like tens of micron. So if you want to have 400 micron, you need like W over L like 10, which is crazy here. So of course, this is not optimized. Okay, this is just a simple structure like this mushroom structure with a typical GST 225 kind of ratio. But it shows that by scaling the contact area, you can go down to here, for example, below 100 micron. If you can get the contact area below like, let's say 400, that means 20 by 20 nanometer, then you can scale that. Okay. But then besides the simple scaling, you want to improve, okay, the thermal structure engineering. So here, the mushroom structure is easy to fabricate because here you just need to pattern the contact wear for the plug, and then you deposit this GST material, you know, across the wafer, right, by simple deposition. But this is not the best way from the thermal standpoint, right? Because here you generate the heat here, and then the heat will, you know, dissipate in different, you know, directions. So why not we confine the heat within this contact wear, right? So here, if you can have the GST material within this contact wear, then the heat is generated here, and then this is the insulator. Everything is confined. This is called the confined structure, right? Confined. Then the heat will concentrate here. Then that will help, right? You don't need some large current because the heat is, you know, more local. So here you see that some data, right? The same plot. If you use structure B, which is this confined cell, without changing the material composition, simply by doing that, then the requirement on the reset current, you know, reduce almost 50%, right? So this is a better design. So with this concept, actually people have demonstrated, I believe this is from Samsung maybe, yeah, at the Symposium VLSI 2010, demonstrate a really scaled confined cell with here the dimension like 7 nanometer by 17 nanometer. And then the phase change material is confined in this local space. Okay, you see some images from the TEM. So then the research community even did some experiments to look at the ultimately scaled device. Okay. So here by this one, you still need some advanced lithography to define this region and then do the edge and so on. So industry can do that, but university is difficult, almost impossible to pattern like 7 nanometer in any university, right? So, but then the research groups in the university came up with some interesting idea to use the carbon nanotube as a conductor, okay? Because carbon nanotube with metallic phase, I mean, there's some orientation. So some carbon nanotube could be conducting. So anyway, so the idea is to here to build this natural device. Okay, you have a carbon nanotube here, and then we'll burn. You will apply in the experiment. You are going to burn the carbon nanotube by passing a large current. So the carbon nanotube will be burned, and you create a local gap. Okay, here, and then you deposit the GST material over here. So basically, you create a local GST gap. And then because the carbon nanotube, the diameter is only like 1 nanometer, 1.5 nanometer or so. So you get this nano gap. You have two electrode, which is the carbon nanotube, and then here in the middle, within the gap, you have some like GST material. So you get the ultimate scaled device. Of course, this is not for integration. In integration, I mean, you will not be able to use carbon nanotube to make a large array or something. But for single device, I mean, for fundamental research, this is a good approach. So you see that with this approach, the currents, reset currents, go down to like even 1 micron, okay, with this ultimately scaled, like maybe 2 nanometer by 2 nanometer device, okay. So here, this is the programming curve, and also they demonstrate some like endurance up to 100 cycles. Of course, it's not very reliable, but it works functionally, right? So then the current is small, less than a few micron, and then therefore the red power is less than 100 femtojoule, which is good. If you can, scale this down to like a 2 nanometer by 2 nanometer, okay, using the conventional fabrication method, which is still impossible today. And I mean, industry cannot make 2 nanometer by 2 nanometer contact. There's no way. So from the lithography, even with the EUV, there's no way. Okay, today, as of today. But anyway, so if you do this, okay, this paper surveyed the scaling trend from the conventional approach, conventional reported data from the literature, in terms of the, let's say, reset current as a function of this contact area, right? And then the reported data, because most of the data, has like a 100 by 100 nanometer or 50 by 50 nanometer diameter. Then even with consider the roadmap projection, okay, here. But if you plot that carbon nanotube data, that will be here, okay. It's on the scaling trend, right? If you can do, let's say, 2 nanometer by 2 nanometer, then you can get less than 5 micron, or even less than that, maybe 1 or 2 micron current. Then that's ultimate, okay, scaling for the phase change memory. Of course, this is just from the programming current power consumption point of view. We don't know. I mean, at that scale, how about the reliability, like endurance, retention? Nobody has demonstrated the good results at that dimension. So, but anyway, this is for the scaling. So the power consumption is too high currently, even for that 30 by 30 nanometer. So to make it competitive, you have to scale down that at least maybe somewhere here, okay, tens of micron. So that means 10 by 10 nanometer. Okay, so then this is the current scaling challenge. Multi-level, we already mentioned that. So here, basically you can operate on this programming curve, especially in the reset, right? You can stop at different levels depending on the programming current or reset current, right? So larger reset current, you're going to create a larger volume. And then in the, let's say, also, besides the amplitude, okay, you can also do the timing control. So here, so let's say the volume control is due to the different amplitude. And then for this part, okay, you can do the timing control. When you change the slope of this set pulse, you can create different resistance states as well. So you can control the falling time. You can control the amplitude to create the multi-level states. Okay, it's basically by playing with the volume of this amorphous region compared to the crystalline region. Because on-off ratio is large, so on-off ratio over like 100. So you could insert a few levels in between. So here you see that here are some data from this IBM paper long time ago. So you can utilize the set region or gradual set or reset region. You can get 4 levels, 2 bits. Of course, then you will have some variations from cell to cell or even from cycle to cycle. So you have those distribution in terms of the resistance. Okay. So here, if you want to have more levels in between, for example, if you want to have 16 levels in between, then that will be more difficult, right? So it's the same issue as the NAND flash, right? If you want to have, let's say, multi-level 2 bit per cell, 2 TLC, 3 bit per cell, or QLC, 4 bit per cell, then you have to tighten the distribution. So to tighten the distribution, always write and verify. So in the NAND flash, we have the ISPP, right? The incremental step programming. So here, similarly, you have to do the write and then read and then verify, means reprogram. So here, if you do that, you see you can tighten the distribution here, right? Without any verify pulse, you have a spread in terms of resistance. And then after tightening by multiple pulses, you can make it pretty tight in terms of distribution. So this is doable with the phase change memory. I would say 2 bit per cell is easily doable, and 3 bit or 4 bits is tough. You need a very aggressive write and verify. Then in terms of reliability issues, so first of all, the retention, right? So especially, let's say, the spontaneous crystallization, because as I said earlier, the atoms tend to move to the ordered location. That means the device tend to move, let's say, from the high resistance states to the low resistance states. If you have some temperature, okay, then that will accelerate this recrystallization due to the spontaneous process. So here again, you have to measure this at different temperature, right? And do this 1/kT plots. I will skip this. I've talked about that before many times. You have to do that and get the slope, which is the activation energy, and then you extrapolate. Okay. So this is the same issue as R1 as NAND flash. But also in the phase change memory, there is a unique drift behavior, which somehow is opposite. The resistance in the low resistance state also tend to go to higher resistance states. You see that here. So the resistance tend to go up. Okay. So then this is due to some relaxation behavior. And okay. So let's skip this one. Or already talk about this. This is the thermal activation energy. So this is the equation, and you can do that. And then here, I want to talk about this one, the resistance drift over time. This is a known issue for the amorphous, especially for the amorphous phase. Okay. I would say for the intermediate phase. Okay. Then you will have this tendency to increase the resistance over time, especially in the amorphous states here. So you have some slope, and this is typically modeled with this power law. Okay, like the resistance is function of this resistance as initial and T to some factor here. So this is a problem for multi-level operation, right? Because in the middle states, it tend to drift over time. Then the other challenge for the phase change memory, this is also unique to the phase change because the mechanism is thermal, right? So then you may have the thermal crosstalk disturb. So here you see that if you have two adjacent cells, then you are going to program this cell, and then you will have some temperature profile there, right? High temperature, and then you will dissipate the heat. And then, so here the temperature will be high, right? Let's say 500 C. But when the temperature, goes to the adjacent cell, maybe it become like 200 C. So 200 C will help this one to crystallize, right? If this one starts with a high resistance state, and this 200 C will help this one to do this, okay? Even though you are operating here to reset, that means you are going to change from the low resistance state to the high resistance state. But this temperature, this is what you need, 500 C there. But then when the temperature drops to 200 C, if this cell happens to be in the high resistance state, this 200 C will help the HRS to gradually go to the LRS, right? So if you keep doing this, right, you create the thermal stress time. For example, here, if you use a programming pulse like 100 nanosecond, if you repeatedly do this like 10 to the power 9 cycles, that means you are going to get 100 second total thermal disturb time or stress time to this guy. So 100 seconds, then you have to go back to this 1 over KT plot to look at the retention time for this guy. Okay. So here in this particular example, right? So here 100 seconds. Okay, this is second. 100 second is here. Oops. You see that 100 second, it can sustain the temperature here. This one, 24 1 over KT. You have to convert back to the degree C, which is 210 degrees C. So that means this cell can sustain 100 seconds at 210 C. So that corresponds to 10 power 9 cycles you are doing here. And then this device, after that, this device will change from the high resistance to the low resistance state. Okay. So the maximum temperature allowed on the labeling cell is this number. Of course, this depends on the thermal property, right, between the cells and also the distance between the cells. As you scale down the technology node, right, then you are going to make those cells closer to closer. Then this temperature gradient will easily penetrate to the neighboring cell. That will cause this disturb. Right? And then the endurance, okay. So there could be different failure modes as you cycle the device. We measure the resistance, high and low, high and low, right? And then here, in this example, then after 10 to the power 9 cycles, you see that the high states will keep decreasing and eventually stuck at the low states. This is the most common failure mode. And this is because the GST material is kind of intermixed with the adjacent material due to the so many thermal cycle. So the material will have some diffusion to the electrode, even to the the barrier material. And sometimes the device may stuck here at high state in some cells. This is because after so many thermal cycle, due to the material adhesion problem, may create a volume there, right? So here you have this stone stuff. And then sometimes if you have high temperature and then make the atoms move all away, then if you create a void in this location, then that's like, a gap, air gap, then the current will not go through, then you're stuck at the high resistance state. Okay, if you have this void there. So typically the endurance could be from like 10 to the power 6 to 10 to the power 9 for the phase change memory. So it's a little bit higher than the NAND flash. Okay, so then the last part, array level integration. So here the phase change memory, if you want to integrate into the array, first option is 1T1R, right? You need the transistor. So here, then the transistor, you can have the MOSFETs 1T1R, but as mentioned earlier, you need high reset current, typically hundreds of micron. So the access transistor, W over L, is larger than 1, right? So that makes the cell area up to like 40 F² or even 50 F² because W is large. So typically here you have the transistor down here, and then here you have the contact wire to the drain, and then you make this mushroom structure here, right, on top of that. So here then the alternative option is to use BJT. It's still a transistor, but it's bipolar junction transistor. Nowadays we do not talk about this too much because not many foundries are offering this at advanced nodes. But at least that's one advantage for BJT. That is the drive current given the same dimension is higher than MOSFET because here the phase change memory is too power hungry. So the BJT given the same width of the transistor will provide more current, okay, than MOSFET. So then that will help, okay, with the cell size. You don't need as large as MOSFET's channel width to provide the current. So one example, maybe we'll show that later. So ST Microelectronics, which is a company in Europe, their business mostly is on the automotive electronics, but they have the phase change memory process. And then in their latest a platform like 28 or 22 nanometer, they use BJT actually for the phase change memory. So here, this is a simple comparison. I will skip. We already talked about the benefits of BJT, right? Is to have higher drive current. Therefore, you can make the cell a little bit smaller than the MOSFETs 1T1R. So ultimately, you can do the cross-point array, right, with the selector. So we talked about cross-point array earlier. So then the phase change memory, right? If you do the cross-point array, you get the ultimate like 4F square for the 2D planar, like one layer cross-point array. So here, what you can do is to integrate the phase change memory with a diode. Diode is like a selector, right? But it's only one directional, unidirectional, p-n junction, basically, right? But this one works because phase change memory, as I said earlier, is unipolar. Okay, it's not bipolar. You just need to pass the current in one direction, but with different amplitude. And this is unlike R1, you have to apply positive and negative voltage or current. So for this one, you only need one direction. So you can use diode because diode only allow one direction, right? P-n junction. So that's why in the early demonstrations, for example, this paper from Samsung in IEDM 2011, it demonstrates the 1D1R. You can create 1D1R because it's one diode, one resistor in 20 nanometer technology node. And here the p-n junction, this p-n junction could be the silicon p-n junction from the substrate. Okay. And here the half pitch is 20 nanometer. Okay, the half pitch is 20 nanometer. F is 20. That means here in this paper, then this F is 20. So here, this is the early days of the, let's say, history of the phase change memory development by the community. And here we do have some demonstrations. Even as early as 2002, there's this paper at 180 nanometer, 1T1R phase change memory. Right, this is more than 20 years ago. And here, for example, 2008, there's already like 90 nanometer, 128 megabit 1T1R array. And then I believe here in the 2009 to 2012, companies like Micron, Samsung, all have this prototype ready. And here, for example, this one I believe is from Micron, 1 gigabit, 45 nanometer process. And then the one I just showed, the Samsung, this 20 nanometer cross-point array, actually integrate 8 gigabits phase change memory there. This was already 12 years ago. And Micron and Samsung actually had some volume production at that time. Even I remember there was a news, some Samsung early days of some of those smartphones use the phase change memory module. In the motherboard, there's a phase change memory chip in one of the early smartphones around 2012. So here, this is a paper I mentioned. This is a milestone. So here, then you can look into more details here. And so cell size is around 14 by 14 nanometer square, right? Because 4F square, 20 by 20, and then 4F square, 40 by 40. It's a diode collected. And the total chip size, and then the power supply voltage, and then the interface is LPDDR2 at that time. Okay. And then here you see the set is like 150 nanosecond. And then the reset must be faster because, as I said, the quench process is faster. So they just care about the slower one, which is a set, is 150 nanosecond in this case. And then here you see the total internal, let's say I/O bandwidth is 40 megabytes per second, but with the external DDR LPDDR2, you can do 133 megabytes per second, right? So then this is the total chip. So you do see some pumps here because even though the voltage, I/O voltage is, let's say the power supply 1.8 volts, but I believe on chip it generates some high voltage, maybe 3 or 5 volts to program the phase change to provide this current. Okay, so then here is the story after 2012. Samsung, okay, stopped their development on this phase change memory, even though they have this 8 gigabits. And even at the same year, IDM 12, Samsung reported the OTS selector. Okay, if you recall, OTS is this organic threshold switch, which is the selector device, bidirectional selector. Okay, and then in 2015, Intel and Micron announced the 3DX point. We already discussed that in the earlier lecture. And then this product lasted for like a few years, and then they stopped the commercial product in around 2020 and 2022, respectively. Intel actually is 22, Micron is 20. So then in 2017 and 18, SK Hynix started the similar stuff, okay, cross-point array, phase change memory with OTS selector, but no volume production since then. So those memory companies like Micron, SK, they are interested in the standalone memory, storage class memory maybe. Okay, but still the business is not clear even as of today, right? So we don't know if the business-wise there will be benefits. But anyway, so since 2018, then the phase change memory has also become, let's say, attractive for embedded space. Okay, embedded non-volatile memory. For example, ST Microelectronics, as I mentioned earlier, right? They want this for the automotive microcontroller, right? So you need the embedded non-volatile memory. So the same market as the R1 we talked about earlier, right? So ST bet is on the phase change for the same market. Okay. TSMC has also phase change memory developments internally. They had the 40 nanometer phase change memory, but not in the volume production, and as of today. So because maybe compared to the R1, the phase change memory still cost is a little bit higher because the material is a little bit weird, right? Compared to the hafnium oxide R1, and also the power consumption may be a little bit larger. If the market is similar, right, then the embedded non-volatile memory for the automotive microcontroller, then if TSMC has R1 already in the production, maybe they don't want to invest more in the phase change. But at the beginning, like back in 2018, even earlier than that, TSMC has both, okay, on their table, like R1 and phase change. But R1 took off, phase change is still on the table. Okay. So what is new here? This is new. In 23, okay, just last year, 1 or 2 years ago, there's a renaissance of the phase change memory. So the selector-only memory is coming back and reported by SK Hynix. And this year, I think Samsung also has a paper at IEDM. So this draws industry's recent attention again. So then let me quickly show you what is those recent, progress here. So first of all, we mentioned this ST microelectronics. They have this embedded phase change memory for the automotive, right? Microcontroller application. So here, this is at IEDM 2020, and they have the 28 nanometer FDSOI platform for this phase change memory. So I believe here they use BJT, as I mentioned earlier, BJT as the transistor for the 1T1R. And here are some nice images along the bit line direction, along the word line direction. Okay. And then the cell size is 0.019 micrometer square, 1T1R. You know this number. Do you see this number familiar to you? This is the same as 3 nanometer S1 from TSMC, the cell size, the same size. But this is a 28 nanometer platform, 1T1R. But that T is BJT. Okay. So this could be attractive, right? So you get the density at 3 nanometer SRAM, but in this 28 nanometer platform, right? So here, this is a chip by the ST Microelectronics, and you see 16 megabytes, and then here you see the window, right? So you really care about this like tail. This is at 1 ppm. 1 ppm is 1 per 1 million, right? You need the real tail. Still, there's a window, okay? And then here the endurance, they report the endurance up to 10 million cycles, 1E7 cycles. So pretty good. So here is a quick summary. So here, even before this IEDM 2020, ST has another paper at IEDM 2018. At that time, the only difference is that the 1T1RT is a MOSFET, but that MOSFET is a 5-volt I/O MOSFET. Okay, then they changed to the 5-volt I/O BJT in the IDM 2020. That enabled the scaling. You see from the bit cell size as a same platform, 28 nanometer platform FDSOI, and then here you see that the cell size shrink. And in terms of f square, if you want to if you use f as 28, then you see that shrink thanks to the BJT there. And then, but here, then the on-off ratio decreased a little bit, but still you see the current is pretty high, 300 micron, right? And the endurance like 1E6 or 1E7, and then retention kind of okay. And also TSMC, as I said, in the early days, it also has the development of this phase change, and then they have 1T1R, T is a MOSFET, okay. So then, yeah, they have some numbers there, pretty on the same bar. Yeah. Okay, so then this is the latest progress in this field. Selector only memory. Okay, so this is a key idea. So previously we have this 1S1R, where the S is OTS. This is the same as the 3DX point by Intel and Micron. Okay, you have the selector, which is the OTS threshold selector. Combine that with the phase change memory. Both are chalcogenide material, but there are some subtle difference, which I don't know because that's the secret of that industry. And so I don't know the exact composition. What's the difference between the phase change and the OTS? Nobody knows actually. I mean, outside that circle. So, but anyway, so here the key idea is to get rid of the phase change memory at all. They want to use just the selector as a memory. This sounds weird because selector is a selector, right? Selector actually is not a memory. If you recall my statement before, selector ideally is a switch. Switch is not a selector. Like transistor is a switch, right? Switch, you switch from 0 to 1, but after you remove the voltage, then the 1 goes back to 0. Okay. But the memory, you need that 1 to be 1, right? So here there is a catch here, which is very intriguing to me. Nobody knows the mechanism, even as of today. This is still under debate. But somehow for example, the researchers from IMEC discovered this, and also that SK Hynix also followed this. So here you see that the selectors turn on voltage, okay, only selector, okay, without the phase change memory. So the selectors turn on voltage has a history effect. That means, okay, the turn on voltage here is a selector, but the turn on voltage depend on the device's prior state, whether the device has gone through a positive pulse or negative pulse. Or in other words, let's put it this way, okay. If, let's say, you only have the selector, okay, only selector, the turn on voltage is the indicator of the, let's say, memory state. So here, if you apply a positive pulse to this selector, okay, and after that, you do the read operation. In the DC sweep, you're going to sweep this. But after the positive pulse, when you sweep, the turn on voltage is smaller. So here, this VTH small. Oops. And then if you apply a negative pulse to this selector, the VTH when you turn on will be large. So when you read, you can read somewhere in the middle, okay? So if the device, let's say is 0, or let's say it's 1 and 0, right? You rely on the turn on voltage difference between the 1 and 0 states. And then that turn on voltage is a function of your programming pulse direction. It's kind of weird, but this is very nice because the device can cut off the sneak path because it's a selector. Here you see below this voltage, then the current is very negligible. And then when you read, you bias somewhere in the middle. If the device has been programmed with a positive pulse, then at this read voltage, it will turn on. You will read out large current. If the device is programmed or erased with 0, with negative pulse for 0 state, then it will remain off. But after the read operation, then the device will, because the selector, it will go back to 0 current. Only when you bias the device above this voltage, turn on voltage, you will read out. So it's pretty nice. And you get rid of the phase change memory. Therefore, you can shrink the cell size, at least height. You reduce the complexity of the integration, reduce the cost. And also, because you get rid of the phase change memory, you improve the endurance as well. Because one challenge for this OTS with the phase change memory, because sometimes they will intermix after cycling. So you get rid of the phase change, only OTS, endurance will improve. And also I heard that the current, yeah, that's true here, also reduce. You see here only 15 micron for the programming compared to the 300 micron of the phase change. So here SK Hynix demonstrated a very nice prototype chip, I think from last year's IEDM and this year's VLSI. And Samsung, I think, will also showcase their stuff at this upcoming IEDM 24. So at least from SK's chip, it's a 60 megabit chip. Sorry. The total chip size is 64 gigabits. It's pretty large. This is a very large chip. And the F is 16 nanometer. Okay. And then you see the red pulse only like 20 micron. This is one of the big challenge, as we mentioned, for the phase change. And then retention seems okay, and endurance 1E7 seems reasonable. So if this is true, I think the phase change memory, let's say a selector only memory may have some, attractiveness for certain applications. This may come back. At least SK and Samsung are heavily investing in that right now. Okay, so this is the summary. And I already said that here phase change memory actually mature in terms of the manufacturability. So foundries, TSMC and ST, they have the process at 40 and 28 nanometer for embedded applications, 1T, 1R. The T could be BJT, okay. And then for the standalone memory, right? So Intel and Micron tried, right? There's cross-point array, and but then the business failed. But as I just said, the select-only memory may give this phase change memory business a new birth, or let's say renaissance. So fundamentally, the challenge here, right? So for the phase change memory, then the reset current is still too high. But since the selector only, if you get rid of phase change memory, but with the selector only, but then you can reduce that current. Okay. So the selector only memory is similar like phase change because I said selector, the OTS material is still chalcogenide. Maybe the ratio is not GST 225, or maybe there are some doping. I don't know. Actually, nobody knows what's inside. But overall, it's similar to the phase change memory. It's still chalcogenide material. Okay, so any questions? All right, so then we will stop here today.